There's a quiet hum in the depths of space, a whisper so faint, it slips past most telescopes and fades into the cosmic background. But every so often, something cuts through the silence. A signal not from stars or planets, but from vast, drifting clouds of interstellar plasma, glowing like ghostly tapestries against the black. These clouds shouldn't be talking to us. And yet they are strange pulses, unexplained bursts, patterns that defy logic, each one a cosmic cipher waiting to be cracked. What if these signals aren't just random noise? What if they're intentional, even purposeful? From flickers that repeat with eerie precision to tones that shift in ways physics can't explain, the universe seems to be hiding messages in plain sight. Imagine standing under a sky alive with invisible voices, not the familiar crackle of radio stations or satellite chatter, but something older, wilder, a language woven into the fabric of space itself. For decades, astronomers have caught fragments of this dialogue, signals that arrive without warning, linger just long enough to baffle scientists, then vanish like echoes. Some last mere milliseconds, others loop for years, cycling through sequences that feel almost deliberate. The closer we listen, the more questions arise. Are these the echoes of collapsing stars, the fingerprints of unknown physics, or could they be something far stranger, a phenomenon we haven't even named yet? This is where the mystery pulls us in. Over the years, 25 of these signals have stood out, each one a puzzle box of cosmic proportions. Some line up with distant galaxies, others seem to come from nowhere at all. A few even repeat on schedules so precise, they've spawned theories ranging from alien megastructures to ripples in the fabric of reality. And here's the thrilling part, every time we think we've figured them out, the universe tosses us another curveball. So today, we're diving deep into the enigma of these interstellar whispers. We'll trace their paths, unpack their secrets, and follow the trail of clues they've left across the cosmos. Buckle up, because by the end of this journey, you'll never look at the night sky the same way again. The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope. The night sky was calm, the equipment humming softly as it scanned for whispers from the cosmos. Then, just after 10:30 in the evening, the machine printed out a sequence of letters and numbers that would haunt astronomers for decades. 6 big characters, 6EQUJ5, blazing onto the page. Researcher Jerry Amon circled them in red ink, scribbling one word next to it that said it all. Wow, the signal was strong, impossibly so, 30 times louder than the usual cosmic background noise, and it lasted a full 72 seconds before vanishing without a trace. It came from the direction of the constellation Sagittarius, where no known stars or planets could explain it. And here's what makes it unforgettable. It hit the exact frequency scientists had predicted an extraterrestrial signal might use, the hydrogen line at 1420 MHz, a universal marker for cosmic communication. Since that night, the WOW signal has been hunted like a ghost. Astronomers have pointed telescopes back toward Sagittarius thousands of times, listening for a repeat. Not a peep. Some think it was a one-time cosmic burp, maybe a comet's hydrogen cloud flaring up, though none were known to be in that exact spot. Others argue the signal was too clean, too purposeful to be natural static. The way it rose and fell matched what you'd expect if a distant transmitter briefly swept past Earth's field of view, like a lighthouse beam glancing across a ship at sea. And then there's the eerie silence that followed. If it was aliens, why haven't they called back? Or worse, what if they did and we just missed it? The mystery only deepens when you consider the numbers. To reach us with that intensity, the source would need to be millions of times more powerful than anything humans have ever built. A civilization capable of that wouldn't just be advanced, they'd be monumental. And yet, after nearly 5 decades of searching, we've found nothing like it again. No repetition, no pattern, just that one tantalizing blip. It's as if the universe handed us a single puzzle piece, then hid the rest of the box. Today, the WOW signal stands as a cosmic riddle, equal parts inspiration and frustration, proof that something extraordinary happened out there, but refusing to tell us what. Maybe that's why it still captures our imagination. It's not just a signal, it's a dare, a challenge to keep listening, to keep pushing, because the next time we hear that whisper from the dark, we might finally be ready to understand it. 17 years after the WOW signal, another mystery punched through the cosmic silence, this one so powerful, it rewrote the rules of what we thought possible. In 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through old data from the Parkes radio telescope in Australia when they stumbled on something extraordinary. A burst of radio waves so intense, it blasted out more energy in 5 milliseconds than our sun emits in 30 days. They called it the Lorimer Burst, and it sparked a revolution in astronomy. Unlike the steady hum of pulsars or the predictable pulses of quasars, this was a cosmic scream, loud, sudden, and utterly alone. What makes this burst unforgettable isn't just its raw power, but where it seemed to come from. The signal's dispersion, the way its higher frequencies arrived slightly before the lower ones, suggested it had traveled billions of light years, passing through thick clouds of interstellar plasma along the way. These clouds, often called the fog of space, are usually silent, but under the right conditions they might act like cosmic lenses, bending and magnifying signals in ways we barely understand. Some theories suggest plasma clouds could even split a single burst into multiple echoes, turning one cryptic message into a chorus of distorted whispers. Yet the Lorimer burst refused to repeat. Despite years of monitoring, no follow-up signal ever came. That left scientists grappling with a paradox. How could something so energetic happen just once? Most cosmic phenomena, supernovas, magnetars, colliding black holes, leave behind evidence or recur over time. But this, it flashed into existence and vanished like a match struck in a dark room. Some argue it might have been the death cry of an exotic object, a neutron star collapsing into a black hole, or a magnetar's catastrophic rupture. Others whisper about more speculative ideas, cosmic strings vibrating through space-time, or even artificial beacons from civilizations too distant to comprehend. The real puzzle lies in the plasma itself. These drifting clouds are more than just static backdrops. They're dynamic, turbulent, and full of charged particles that can twist signals beyond recognition. A burst passing through might emerge distorted, its origin obscured, its true nature hidden. Imagine shouting into a storm your voice carries, but the wind tears it apart. That's the challenge with fast radio bursts. Even when we detect them, the interstellar medium scrambles their story, leaving us to piece together fragments of a narrative we don't yet understand. What's clear is this: the Lorimer burst ripped open a new chapter in astronomy. Before it, no one imagined such fleeting, violent signals could exist. Now, hundreds of fast radio bursts have been recorded, each one adding layers to the mystery. But that first burst, the one that started it all, remains in a class of its own. A flare of energy without a cause, a message without a sender, a cosmic event so brief and brilliant, it forces us to question everything we know about the universe's hidden voices. And the most thrilling part, we're only just beginning to listen. Some signals don't just whisper, they return. That's what makes SHB 02+14 so unsettling. Discovered in 2003 by SETI Home Computing Project, this wasn't a fleeting blip but a recurring presence, pulsing near the constellation Pisces at 1420 MHz, the same haunting frequency as the WOW signal. At first glance, it seemed like the breakthrough scientists had waited for, a repeating pattern in the void, a possible beacon in the dark. But the closer they looked, the more it refused to make sense. The signal drifted, not in the steady way a planet or star might shift due to motion, but in erratic, jagged hops sliding up and down the radio spectrum like a station tuning itself. Natural cosmic sources don't behave this way. Pulsars spin with metronomic precision. Quasars emit predictable jets. It wobbled. Some argued it was interference from Earth, maybe a satellite or passing aircraft, but the signal persisted over years, always returning to the same patch of sky. Others suggested plasma clouds might be to blame. These turbulent, charged regions of space can bend and scatter radio waves, distorting their frequencies as they travel. Picture a lighthouse beam passing through a storm. The light still reaches you, but fractured, warped, its original signal obscured. Yet even that explanation leaves gaps. If plasma interference was twisting SHB 02 plus 14A, why didn't other signals from the same area show similar distortion? And why, despite dozens of follow-up observations, has no one pinpointed a clear source? The region it emanates from is eerily empty. No nearby stars, no known exoplanets, just the sparse glow of interstellar gas. It's as if the signal is being broadcast from nowhere, or perhaps deliberately relayed through something we can't see. Theories spiral from there. Could this be an alien transmitter, its signal drifting as its home planet orbits a distant star? Might it be a natural phenomenon we've yet to classify, a cosmic object interacting with plasma in ways that defy our models? Or is it something stranger, like a malfunctioning probe or a relic from a long-dead civilization, still transmitting on a loop across the millennia? What's undeniable is the signal's persistence. While other mysteries fade into static, SHB 02 plus 14 lingers, a riddle wrapped in interference. It challenges our assumptions about how the universe communicates and whether we're truly alone in listening. Every time it repeats, it offers fresh data and fresh frustrations. Because in the end, the greatest puzzle isn't just decoding what's being said, but figuring out who or what left the radio on. Deep in the archives of cosmic mysteries, there's a signal that blurs the line between science and science fiction. A transmission that arrived in 2001, seemingly answering a message we'd sent to the stars 27 years earlier. It all traces back to 1974, when astronomers at the Arecibo Observatory aimed a powerful radio burst at a cluster of stars 25,000 light-years away. The message was a human calling card encoded with our DNA structure, a sketch of our solar system, and even a crude image of a person. It was a shot in the dark, never expected to get a reply. Then, in August 2001, a crop circle appeared in a field near England's Chilbolton Observatory, a near-perfect replica of the Arecibo Message, but with eerie alterations. The DNA helix twisted differently. The solar system diagram showed an extraplanet, and where the human figure once stood, there was now a being with an oversized, elongated head. But here's where it gets stranger. Just days before the crop circle's discovery, a team of researchers claimed they detected a radio signal from roughly the same region of space Arecibo had originally targeted. The signal's structure mirrored the 1974 message, same frequency, same pulse pattern, but with those same bizarre modifications seen in the crop circle. Skeptics pounced immediately. Crop circles, after all, were well-documented hoaxes, and the radio signal, it could have been interference, a prank, or even a plasma echo. Because here's the thing about plasma clouds, they don't just distort signals, they can replay them. Under the right conditions, dense pockets of interstellar plasma act like cosmic recording devices, bending and bouncing radio waves in ways that create delayed, warped copies of the original transmission. Imagine shouting into a canyon and hearing your voice return minutes later, slurred and fragmented. That's what might have happened with the Arecibo response. Our 1974 message could have hit a plasma cloud, ricocheted, and eventually found its way back to us, twisted just enough to feel alien. Yet the puzzle doesn't end there. The timing was uncanny. Why would a plasma echo arrive precisely when a crop circle mimicking the message appeared? And why did both the signal and the crop circle contain the same subtle changes? Even if you dismiss the crop circle as human-made, the radio signal's anomalies still defy easy explanation. Some researchers argue the plasma cloud theory doesn't account for the signal's precise structural tweaks, which resemble intentional edits rather than random distortion. Others counter that we still don't fully understand how plasma reshapes radio waves over interstellar distances. The debate rages because it strikes at the heart of a bigger question: how do we recognize intelligence in the cosmos? A repeating signal might be natural, a mathematical sequence could be coincidence, but a message that mirrors our own then alters it with purpose. That's harder to shrug off. Whether the Arecibo response was a cosmic echo, a hoax, or something more, it remains a masterclass in ambiguity, a signal that teases us with the possibility of conversation while withholding the certainty we crave. And perhaps that's the lesson. In a universe where plasma can mimic voices and stars can bend light, the line between noise and message isn't just thin, it's shimmering, shifting, and alive with secrets. Of all the cosmic signals that tease us with their mystery, few are as stubbornly puzzling as FRB 121102. Unlike the one-off blast that defined earlier fast radio bursts, this one did something extraordinary. It came back. Not just once, but over and over, like a clockwork pulse from the depths of space. Discovered in 2012 at Puerto Rico's Arecibo Observatory, it shattered the assumption that fast radio bursts were singular, catastrophic events. Here was proof that some of these cosmic screams weren't dying gasps, but persistent voices in the dark. The real breakthrough came when astronomers pinpointed its origin, a tiny, turbulent dwarf galaxy 3 billion light-years away. That alone was a revelation. Dwarf galaxies are cosmic backwaters, lacking the massive stars and dense stellar nurseries we'd expect to produce such energetic signals. Yet there it was, flickering from a place where nothing should have been capable of generating such power, and the patterns it emitted, they defied every textbook. Most cosmic signals fade predictably, their energy dissipating like ripples in a pond. FRB 121102, though, flared with erratic brilliance, sometimes a rapid-fire staccato of pulses, other times long, mournful wails, as if the source itself was alive with variability. This is where interstellar plasma enters the scene. Those vast, drifting clouds of charged particles might hold the key to the signal's strangeness. Picture a beam of light passing through a frosted window. It scatters, distorts, emerges changed. Plasma clouds do the same to radio waves, but on a cosmic scale. As FRB 121102's bursts traveled through the thick plasma of its host galaxy, and the even vaster voids between galaxies, they could have been twisted, amplified, or even split into multiple echoes. Some scientists argue this might explain why the signal's bursts vary so wildly in strength and timing. What if we're not hearing the original signal at all, but a funhouse mirror reflection, warped by its journey through layers of cosmic haze? But the implications go deeper. If plasma acts as a lens, magnifying or obscuring these bursts, it raises a tantalizing possibility. Could other repeating signals be out there, hidden because their paths don't pass through plasma that bends them our way? It's like standing in a forest, hearing only the birds whose songs happen to bounce off nearby trees. The rest might be calling too, their voices lost in the open air. The most unsettling theory, though, revolves around the signal's persistence. Natural cosmic events, neutron star collisions, black hole births, don't usually repeat on human timescales. Yet FRB 121102 has been active for over a decade, flaring up with no discernible rhyme or reason. Some researchers speculate it could be a magnetar, a highly magnetic neutron star caught in an endless cycle of quakes and eruptions. Others cautiously wonder if it's something more deliberate. After all, a repeating signal is the foundation of any attempt at cosmic communication. It's the difference between a scream in the dark and a knock on the door. What makes this signal unforgettable isn't just its defiance of explanation, but what it reveals about the universe's hidden layers. Plasma isn't just interstellar fog, it's an active participant shaping how we hear the cosmos. And FRB 121102, it's not just a mystery, it's a test. A challenge to our assumptions about what's out there, and a reminder that sometimes the most profound conversations don't come in clear sentences, but in echoes, distorted and beautiful, waiting for us to decode their meaning. The year 2020 should have been a turning point in the search for extraterrestrial intelligence. That December, astronomers with the Breakthrough Listen project detected a tantalizing radio signal BLC-1 emanating from Proxima Centauri, the closest star system to Earth. At first glance, it seemed too perfect, a narrowband transmission at 982 MHz, a frequency conspicuously free of natural cosmic noise. Even more compelling, Proxima Centauri hosts at least one rocky planet in its habitable zone. The signal's characteristics screamed artificial. Headlines erupted with claims of potential alien contact, and for a brief, electrifying moment, the world held its breath. Then came the twist. As researchers scrutinized the signal, its flaws emerged. BLC-1 drifted in frequency, not smoothly, as a planet's motion might cause, but in abrupt jumps. Stranger still, when they pointed other telescopes toward Proxima Centauri, the signal vanished. The culprit, interstellar plasma. The space between stars isn't empty. It's a turbulent sea of charged particles that can refract, distort, and even amplify radio waves. A faint terrestrial signal, maybe a satellite or ground-based transmitter, could have bounced through these plasma currents, emerging as a false echo from the direction of Proxima Centauri. Picture a whisper ricocheting down a hallway until it sounds like it's coming from another room entirely. But the real lesson of BLC-1 isn't just about false alarms. It's about how fragile our cosmic listening truly is. Plasma clouds don't just obscure signals, they create illusions. A passing microwave oven, a cell tower, even a distant airplane, all could be twisted by plasma into something that mimics an alien broadcast. The universe, it seems, is a master ventriloquist, throwing its voice across light years to toy with our expectations. What lingers, though, is the haunting possibility that we might have missed the real thing. If plasma can fake a signal this convincingly, could it also be masking genuine transmissions? Proxima Centauri's plasma environment is particularly dense, a swirling fog that might scramble or absorb true extraterrestrial signals before they ever reach us. It's like trying to hear a conversation through a thunderstorm. The noise drowns out everything but the loudest, clearest words. BLC-1's legacy is a paradox. It was a letdown, yes, but also a revelation. It forced astronomers to refine their tools to account for plasma's trickery and to confront an uncomfortable truth. The cosmos isn't just silent or noisy. It's a hall of mirrors where every whisper could be a shout or just our own voice echoing back to us from the deep. In the quiet constellation of Hercules, 94 light-years from Earth, a star almost too ordinary to notice suddenly made headlines. HD 164595, a sun-like star with at least one known planet, was the source of a signal so peculiar. It briefly reignited the debate about intelligent life beyond our solar system. Detected in 2015 by the Ratan 600 radio telescope in Russia, the transmission pulsed at 11 GHz, a frequency typically reserved for military and satellite communications on Earth. That alone raised eyebrows, but what really set pulses racing was how the signal behaved. Unlike the random static of cosmic noise, it modulated, shifting in intensity in a way that felt deliberate, almost engineered. Theories erupted immediately. Could this be an alien broadcast, perhaps a leakage from some distant civilization's technology? The star's age, 6.3 billion years older than our sun, suggested plenty of time for life to evolve. Yet skepticism followed just as fast. 11 gigahertz is a noisy band cluttered with human-made signals. Could this have been a satellite's reflected echo or even a glitch in the telescope systems? Then came the strangest twist when researchers pointed other telescopes toward HD 164595. The signal had vanished. No repetition, no trace, just silence. This is where interstellar plasma enters the story. Those vast, turbulent clouds of charged gas don't just distort signals, they can amplify them, bending radio waves into focused beams that hit Earth with unexpected intensity. Imagine shouting across a canyon and having the wind carry your voice directly to one listener while leaving others in silence. Plasma clouds might have done something similar with HD 164595's signal, magnifying a faint cosmic whisper, a passing comet's emission, or a star's magnetic hiccup into something that briefly mimicked intelligence. But there's another, more haunting possibility. What if the signal was artificial, just not alien? Human technology saturates the radio spectrum, and our signals sometimes ricochet off the moon, satellites, or even debris, returning to Earth from unexpected angles. A military transmission or satellite test bounced through space could have been refocused by plasma into a narrow, star-like point. The irony: we might have been eavesdropping on our own echo, mistaking humanity's noise for the universe's signal. HD 164595's mystery endures because it embodies the central challenge of cosmic listening. Space isn't just empty or full, it's active, a dynamic medium where plasma twists and tunes the messages passing through it. Every signal we catch is filtered, reshaped by these invisible currents. So when something unusual drifts into view, we're left grappling with a kaleidoscope of explanations, each as plausible as the next. Was it aliens? Almost certainly not. But the real revelation lies in how easily the cosmos can pretend, how a star, a plasma cloud, and a little human hope can conspire to make us wonder, if just for a moment, whether we're not alone after all. Near the crowded heart of our galaxy, where stars swarm like fireflies in the night, a cluster known as Glimpse C01 has been broadcasting secrets no one can quite decipher. Unlike the predictable rhythms of pulsars or the steady glow of quasars, the signals from this region arrive in chaotic bursts, sometimes sharp and sudden, other times lingering like a hum just at the edge of hearing. Discovered in 2013, these emissions defy every category astronomers have tried to force them into. They don't match the fingerprints of any known cosmic object, and their irregular cadence suggests something far stranger is at play. Theories begin with neutron stars, those dense, spinning remnants of supernovas. Some suggest these signals could be the result of a neutron star plowing through a particularly thick cloud of interstellar plasma. Picture a ship cutting through fog, its wake churning the mist into swirling patterns. A neutron star's immense magnetic field could do the same to plasma, twisting it into temporary structures that emit radio waves as they collapse. These interactions might explain the signal's irregularity. No two plasma clouds are exactly alike, and each collision would produce a unique distortion. But there's a problem with this explanation. The signals from Glimpse C01 don't just vary in intensity, they flicker in ways that don't align with any known neutron star behavior. Some pulses arrive in rapid succession, while others vanish for months before reappearing without warning. It's as if the source isn't just reacting to its environment, but changing it, actively reshaping the plasma around it in real time. This has led to more speculative ideas, like the possibility of a binary system where a neutron star and a black hole orbit each other, their gravitational dance stirring the plasma into frenzied, radio-emitting turbulence. Then there's the location itself. Glimpse C01 sits just 13,000 light-years from the galactic center, a region so packed with stars, dust, and magnetic fields that it's like trying to listen to a whisper in a hurricane. The signals we detect might not even be the original emissions, but echoes radio waves bent and scattered by the dense plasma fog that permeates the area. Imagine hearing a voice through a maze of corridors. By the time it reaches you, it's been reshaped by every wall it's bounced off. That's the challenge with Glimpse C01. The very environment that makes the region so electrically active could also be obscuring the true nature of the source. Perhaps the most tantalizing clue lies in the signal's spectral fingerprints. Unlike most cosmic radio bursts, which fade predictably across frequencies, these emissions sometimes show bizarre, almost artificial-looking spikes, narrowband components that stand out against the background noise. It's these details that keep astronomers awake at night. Are they seeing the handiwork of an unknown astrophysical process, or is there a sliver of a chance that something more deliberate is at work? The conservative answer is always to assume natural phenomena first, but Glimpse C01 tests that patience. Every time researchers think they've pinned it down, the signals shift again, slipping through the cracks of our understanding like smoke. What makes this mystery unforgettable isn't just the what, but the where. The Galactic Center is a cosmic laboratory of extremes, black holes, magnetars, and stars crammed so close together their gravity tangles like vine. If strange new physics is lurking anywhere, it's here. And Glimpse C01 signals might be our first glimpse of a phenomenon we've never imagined, something that could rewrite the rules of how matter and energy interact in the universe's most crowded neighborhoods. Until then, they remain interstellar enigmas whispering from the chaos at the galaxy's core, daring us to unravel their secrets. Tabby's star isn't just another flickering dot in the sky, it's a cosmic rebel refusing to follow the rules. Officially known as KIC 8462852, this distant sun, roughly 1,400 light-years away in the constellation Cygnus, became infamous in 2015 when astronomers noticed something impossible. Its light didn't just dip in predictable rhythms like planets passing in front. It plummeted by up to 22%, in irregular, jagged patterns that no natural phenomenon could easily explain. The internet erupted with theories, the wildest being that we'd found evidence of an alien megastructure, a vast swarm of energy-harvesting panels orbiting the star. But the truth might be even stranger, tangled in the invisible fingers of interstellar plasma. At first glance, plasma seems too flimsy to explain Tabby's star's dramatic dimming. These clouds of ionized gas are diffuse, often thinner than Earth's best laboratory vacuums. But under extreme conditions, like those near a turbulent young star, they can clump, twist, and even form temporary structures dense enough to cast shadows. Picture smoke curling from a candle, forming fleeting shapes before dissolving. Now imagine that smoke is superheated to millions of degrees, threaded with magnetic fields, and stretched across millions of miles. That's the kind of plasma environment that could, theoretically, drift in front of Tabby's star, blocking its light in unpredictable ways. Yet the puzzle deepens when you examine the star's long-term behavior. Over the past century, observations suggest Tabby's star has faded by an astonishing 14% overall, far more than any known star of its type should. Plasma alone can't account for this gradual dimming, leading some scientists to propose hybrid explanations. Maybe a family of giant comets shrouded in plasma-rich debris is spiraling into the star in fragments, creating both sudden dips and a slow, dusty veil. Or perhaps the star itself is undergoing rare magnetic convulsions, stirring its outer layers into plasma storms that occasionally erupt into our line of sight. The most tantalizing clue comes from the dimming's wavelength dependence. When Tabby's star dims, shorter wavelengths blue light are blocked more than longer ones red light. That's the fingerprint of something not solid like a planet but granular like dust or plasma. Yet the particles would need to be microscopically fine, smaller than cigarette smoke, to scatter light this way. And here's where plasma's versatility shines. Under the star's intense radiation, dust grains could become ionized, merging into a sprawling, hazy shroud that ebbs and flows with stellar winds. But even this elegant theory stumbles when faced with the star's most baffling trait, its speed. Some of Tabby's star's dimming episodes occur over days, while others stretch for years. No single plasma or dust model cleanly explains both. That's why some researchers have circled back to more radical ideas, like colossal remnants of a shattered planet, still glowing with heat and trailing plasma from their collisions. Others whisper about theoretical objects, dark matter interactions, rogue black hole debris disks, or even defects in spacetime itself. What makes Tabby's star unforgettable isn't just the mystery, it's the humility it forces upon us. For all our telescopes and algorithms, we're still peering at this star through a keyhole, catching glimpses of a drama we don't yet understand. The plasma clouds that might veil it aren't just obstacles, they're reminders of how much we can't see. Every flicker, every dip is a message written in shadows, waiting for the day we learn to read it fully. And whether the answer turns out to be cosmic weather, celestial wreckage, or something beyond our current physics, one thing's certain, Tabby's star isn't done surprising us yet. The center of our galaxy isn't just a place, it's a storm. A swirling vortex of black holes, neutron stars, and plasma so thick it crackles with radio noise. But in 2020, astronomers caught something new slicing through this chaos. A series of bursts so sharp and sudden, they stood out like screams in a thunderstorm. Dubbed the unidentified galactic center bursts, these signals don't behave like anything else we've heard from the Milky Way's heart. They arrive without warning, sometimes in clusters, other times alone, with gaps stretching from hours to weeks. No rhythm, no repetition, just pure cosmic spontaneity. What makes these bursts so baffling isn't just their unpredictability, it's their birthplace. The galactic center is a maelstrom of plasma, superheated gas churned by the supermassive black hole Sagittarius A. This plasma isn't just background static, it's alive with magnetic fields and turbulence capable of twisting radio waves into knots. One theory suggests these bursts could be sparks from plasma filaments, vast, charged tendrils snapping like whips under the black hole's gravitational strain. Picture a lightning storm where each bolt is a radio burst electrifying the surrounding haze. Yet even that explanation stumbles when faced with the burst's sheer energy. Some of these flashes release as much power in a millisecond as the sun does in a day. If plasma turbulence alone is responsible, it'd need conditions far more extreme than anything we've observed. That's led to wilder ideas, maybe colliding neutron stars hidden behind curtains of plasma, or magnetars, highly magnetic neutron stars undergoing violent quakes. There's even speculation about dark matter annihilation, where hypothetical particles smash together, releasing energy that plasma then distorts into these cryptic signals. The real enigma, though, lies in the silence between bursts. Most cosmic objects with this kind of power, pulsars, quasars, have predictable cycles. They're completely erratic. It's as if something's switching them on and off at random, or maybe we're only catching fragments of a larger signal, sliced apart by plasma's ever-shifting lenses. Imagine listening to a radio station that keeps cutting in and out, leaving you to piece together a song from scattered notes. What's clear is that the galactic center is hiding secrets within its plasma fog. These bursts could be the death throes of exotic objects we've yet to discover, or evidence of plasma physics operating at scales we can't replicate. Every new detection adds another layer to the puzzle, another question without an answer. And that's what makes them irresistible, not just as scientific curiosities, but as reminders of how much chaos and beauty still lurk in our galaxy's stormy heart, waiting for us to listen closer. For years, the hunt for extraterrestrial signals had one golden rule. If it comes from Earth, it's not aliens. Then along came the Puritan's radio burst so bizarre, they turned that logic on its head. Named after the mythical stag-bird hybrid that casts human shadows, these signals seem to straddle two worlds, mimicking cosmic phenomena while hiding a far more mundane origin. First detected in the early 2000s at Australia's Parkes Observatory, Perytons had all the hallmarks of deep space mysteries: milliseconds-long bursts, broad frequency sweeps, and no obvious source. But their behavior was all wrong. Instead of arriving from distant galaxies, they clustered around local sidereal time, as if tied to Earth's rotation. The real shock came when astronomers traced them not to the stars, but to their own break-room microwave oven. The Peryton paradox lies in how convincingly they impersonated cosmic signals. Most human-made interference is constant cell towers buzzing, satellites chattering, but Perytons were fleeting and erratic, just like their interstellar counterparts. The secret: plasma's sleight of hand. When the microwave's door was opened mid-cycle, its escaping radiation could reflect off ionized layers in Earth's upper atmosphere, regions like the ionosphere, where solar radiation strips electrons from atoms, creating a natural plasma mirror. These reflections would then bounce back to the telescope, stretched and distorted by their journey through charged particles. The result was a signal that looked interstellar but was as terrestrial as a cup of reheated coffee. Yet the story doesn't end there. Some Perytons defied even this explanation, arriving at angles or frequencies that didn't match any local source. This led to a wilder possibility. Could naturally occurring plasma in Earth's atmosphere, sudden ionization from meteors, lightning, or even solar storms, create similar echoes without any human trigger? Laboratory experiments suggest yes. Under the right conditions, plasma can act like a celestial synthesizer, taking mundane radio noise and remixing it into something alien. Picture a DJ scratching a vinyl record. The original sound is recognizable, but the output is transformed entirely. What makes Perytons more than just a cautionary tale is their lingering mystery. Even after most were traced to microwaves, a handful resisted explanation, their origins still debated. Could these outliers be evidence of rare atmospheric plasma events we've yet to categorize? Or might they point to something stranger, like transient plasma structures forming spontaneously in our upper atmosphere? The unsettling truth is that plasma, whether in Earth's skies or deep space, doesn't just carry signals. It reinvents them, blurring the line between nature and artifact. In the end, Perytons taught astronomers a humbling lesson. The universe isn't the only ventriloquist. Right here on Earth, invisible layers of charged particles can twist our own noise into cosmic-sounding whispers, reminding us that sometimes the most alien signals aren't from the stars at all. They're reflections, distorted and eerie, bouncing back from the plasma-filled mirrors in our own backyard. NGC 253 isn't your average galaxy, it's a cosmic fireworks display. Known as the Silver Dollar Galaxy for its brilliant, compact disk, it's also one of the closest starburst galaxies to Earth, a place where stars are born at a frenzied pace, 10 times faster than in our own Milky Way. Amid this stellar nursery, something unexpected has been catching astronomers' attention. A series of rhythmic radio pulses ticking away like a lighthouse in the void. Discovered in 2019, these bursts arrive with eerie regularity every 16 days, as if some unseen hand is flipping a switch on and off with cosmic precision. At first glance, the pulses fit the profile of a magnetar, a highly magnetic neutron star spinning so fast its magnetic field whips plasma into frenzy, generating radio waves. But there's a catch. Most magnetars pulse every few seconds, not weeks. This 16-day cycle is something entirely new, a slow-motion heartbeat in a universe usually governed by split-second rhythms. That's where the galaxy's extreme environment comes into play. NGC 253's core is a plasma cauldron, superheated by countless supernova and young, volatile stars. Some scientists suggest these conditions could warp a magnetar's usual behavior. its magnetic fields tangled in the surrounding plasma like a ship's anchor snagged on reefs. The pulses might not be coming directly from the star, but from colossal plasma loops snapping under magnetic tension, releasing energy in delayed clockwork bursts. Yet the timing is almost too perfect. 16 days isn't just a neat interval, it's the orbital period of a potential companion object, something massive enough to tug the magnetar into an elongated orbit. When the star swings closest to this unseen partner, the stress could trigger plasma eruptions on its surface, firing radio beams our way like a spinning flashlight. If true, it'd be the first evidence of a magnetar locked in such a dance, its pulses not just a natural phenomenon, but a cosmic choreography. But there's another, more speculative layer to this mystery. The pulse's precision and power have sparked whispers of a far wilder idea. What if they're not natural at all? Starburst galaxies are prime candidates for advanced civilizations, regions so rich in energy and raw materials, they could theoretically host civilizations capable of harnessing entire stars. The 16-day cycle could align with something purposeful, like a phased energy transmission or a beacon system timed to galactic rotations. Of course, extraordinary claims require extraordinary evidence, and no one's jumping to the alien conclusion yet. But the very fact that such a thought crosses scientific minds shows how deeply NGC 253's pulses defy expectations. What makes these signals unforgettable is how they thread the needle between the known and the unimaginable. They could be a natural phenomenon pushing the limits of plasma physics, or something else entirely, a signpost in the dark waiting for us to decode its true meaning. Either way, NGC 253's lighthouse isn't just blinking. It's flashing a challenge, daring us to rethink what's possible in a universe where even the most familiar signals can still hold secrets. In the crowded stellar metropolis near our galaxy's core, where black holes and neutron stars jostle for space, one signal has defied classification for nearly 2 decades. GCRT-J 1745-3009, discovered in 2003, didn't just flicker like most transient radio sources. It erupted. For roughly 10 minutes, it blazed with the brightness of a pulsar, then vanished as if someone had flipped a switch. No countdown, no fading embers, just a cosmic flare that came and went like a whisper in a hurricane. What sets this signal apart isn't just its abruptness, but its location. Nestled within the galactic center's plasma-choked chaos, it emerged from a region where magnetic fields twist like spaghetti and ionized gas swirls at near light speeds. Most transient signals here are messy, their radio waves scrambled by the environment, but GCRT-J 1745-3009's emission was eerily clean, a narrowband burst that cut through the noise like a laser beam. That precision is what makes it so hard to explain. Pulsars, magnetars, even colliding neutron stars, none of them produce signals this crisp, this fleeting, without leaving behind some trace. This is where plasma instabilities enter the story. The galactic center isn't just a place of violent objects, it's a cauldron of superheated, magnetized plasma, constantly churning and reconfigured by the supermassive black hole's gravitational tides. Under extreme conditions, plasma can form temporary structures, dense knots or current sheets where magnetic energy builds up until it snaps, releasing bursts of coherent radio waves. Picture a rubber band stretched too tight, finally breaking with a sharp ping. Now imagine that band is a magnetic field line, and the ping is a radio burst powerful enough to cross thousands of light years. Yet even this explanation leaves gaps. Why did GCRT-J 1745-3009's burst last exactly 10 minutes? Why hasn't it reappeared in the 20 years since? Some theorists suggest we might be seeing the aftermath of a magnetic reconnection event, a cosmic short circuit where plasma's twisted fields suddenly realign, unleashing pent-up energy. Others propose it could be a failed pulsar, a neutron star whose magnetic field occasionally reignites in brief, unstable flares, the most tantalizing idea. That we witnessed the death throes of an unknown object, something too small, too strange, or too fleeting to fit into our current catalogues of cosmic phenomena. The lingering mystery of GCRTJ 1745-3009 isn't just about the signal itself, but what it reveals about the galactic center's hidden dynamics. Plasma doesn't just obscure signals here, it can manufacture them, turning random magnetic spasms into radio bursts that mimic deliberate transmissions. It's a reminder that in the universe's busiest neighborhoods, even the most enigmatic whispers might just be the sound of space itself, rearranging its chaotic furniture in ways we're only beginning to understand. At the very edge of the observable universe, where galaxies drift like leaves caught in a current, astronomers have detected something unsettling, a faint, ghostly murmur of radio waves that shouldn't exist. These whispers align eerily with the dark flow, a phenomenon where entire clusters of galaxies seem to move in unison, as if tugged by some invisible hand beyond the cosmic horizon. The signals are so faint they're barely distinguishable from background noise, but their persistence has forced scientists to confront a chilling possibility that the plasma at the universe's outermost edges might be humming with activity we don't understand. The dark flow itself is a cosmic anomaly. Since its discovery in 2008, it's challenged our most fundamental assumptions about the universe's structure. According to standard cosmology, matter should be distributed evenly after the Big Bang, with galaxies drifting apart in a predictable, stately expansion. But the dark flow suggests something else, a mysterious gravitational pull originating from outside our observable universe, dragging thousands of galaxies toward it at breakneck speeds. And now, those faint radio whispers seem to trace the same paths, like breadcrumbs leading to a door we can't see. This is where plasma, the universe's most abundant yet enigmatic state of matter, steps into the spotlight. At the boundaries of the cosmos, where space stretches thin and temperatures plunge, plasma isn't just a passive fog, it's a dynamic, shape-shifting medium. Charged particles, accelerated by the dark flow's gravitational tides, could be generating weak radio emissions as they twist and collide. Picture the static hiss of a radio caught between stations, but on a scale so vast it spans billions of light years. If true, these whispers would be the first direct evidence of plasma responding to forces beyond our observable universe, a cosmic shoreline where the waves of something else lap against the edges of our understanding. Yet the implications unsettle physicists. If plasma at the universe's edge is vibrating in sync with the dark flow, it suggests an asymmetry in the cosmos, a fundamental lopsidedness that contradicts the principle of isotropy, the idea that the universe should look the same in all directions. Some theorists scramble to explain it with known physics, proposing that supervoids or quantum fluctuations might mimic the effect. Others dare to entertain wilder ideas, parallel universes exerting gravitational influence, or remnants of a pre-Big Bang structure still echoing through space-time. The most tantalizing clue lies in the whisper's frequency spectrum. Unlike the broadband crackle of most cosmic radio noise, these signals show narrow peaks, subtle, almost musical tones buried in the static. Plasma turbulence alone can't explain such coherence. It's as if something is tuning the emissions, sculpting them into deliberate patterns. Whether that something is a natural process or something far stranger remains one of cosmology's greatest open questions. For now, the dark flow's radio whispers linger at the edge of detection, a siren song from the universe's uncharted frontiers. They remind us that even as we map the cosmos, vast unknowns still loom, shadows moving just beyond the light, waiting for us to listen closer. And every time we point our telescopes toward those distant shores, we're not just searching for answers. We're straining to hear the universe's quietest secrets, whispered in a language we're only beginning to decipher. Hercules X1 doesn't just pulse, it misbehaves. Nestled in the constellation Hercules, this X-ray binary system is a cosmic oddity, where a neutron star orbits a massive companion, siphoning off gas in a swirling, superheated whirlpool of plasma. Normally, such systems are predictable, their X-ray pulses ticking away like clockwork. But Hercules X1, it's full of surprises. Every 35 days, its X-ray emissions suddenly vanish for roughly 12 hours, as if someone flipped a cosmic curtain shut. Even stranger, its pulses occasionally hitch and stutter, speeding up or slowing down in ways that defy the neat rules of orbital mechanics. At the heart of this enigma lies the system's plasma accretion disk, a chaotic, magnetized maelstrom where gas from the companion star spirals toward the neutron star at nearly the speed of light. Most disks behave like orderly funnels, but Hercules X1's is warped, twisted by the neutron star's fierce magnetic field into a shape that wobbles like a spinning top losing balance. Some scientists think this wobble could explain the 35-day blackouts. As the disk tilts, its outer edges might eclipse our view of the neutron star, blocking its X-rays in a rhythmic celestial hide and seek. But the real mystery is the signal's texture. Between those blackouts, Hercules X1's pulses sometimes fracture into bizarre subpatterns, double peaks, sudden silences, even harmonics that sound almost musical when converted into audio. These aren't just random fluctuations, they're too structured, too repetitive to dismiss as noise. That's where plasma's fingerprints become undeniable. The disk's inner regions are so dense with charged particles that they act like a funhouse mirror for X-rays, bending and splitting the neutron star's emissions into distorted echoes. Imagine shouting into a canyon where the walls are alive, shifting to throw your voice back at you in fragmented, unpredictable bursts, the most tantalizing theory. Plasma instabilities, violent, spontaneous rearrangements of the disk's magnetic fields could be sculpting these signals. Picture a river suddenly forming whirlpools where none existed before. In Hercules X1's disk, such whirlpools might briefly focus or scatter X-rays, creating the illusion of deliberate patterning. It's a phenomenon seen in lab experiments with high-energy plasmas, but never before on this scale. Yet skeptics raise an eyebrow at how precisely some patterns repeat. Could nature really mimic such near regularity without some underlying order? The debate cuts to the core of how we interpret cosmic signals. One camp argues we're seeing plasma physics pushed to extremes, revealing behaviors we've yet to model. Another whispers caution. What if we're glimpsing something more complex, like interactions with a third, unseen object, or even plasma structures self-organizing in ways that blur the line between natural and artificial? Hercules X1's greatest lesson might be humility. Even in a universe governed by physics, plasma's sheer dynamism can craft signals that feel intentional, challenging us to tell the difference between chaos and design. Every hiccup, every blackout is a reminder. The cosmos doesn't just follow rules, it bends them, leaving us to untangle what's real from what's merely plasma's elegant trickery. Some cosmic clocks keep time better than the most advanced atomic watches on Earth until they start humming. FRB 1937 plus 21, a pulsar 16,000 light-years away in the constellation Vulpecula, is one of the universe's most precise known timekeepers, spinning 641 times a second with metronomic perfection. Its rhythmic radio pulses arrive at Earth so predictably, astronomers once used them to test Einstein's theory of relativity. But in recent years, something unexpected crept into the signal, a faint, persistent drift, as if the universe itself were subtly bending the rules. This drift isn't random static, it manifests as a low-frequency hum, an almost musical oscillation that warps the pulsar's otherwise razor-sharp pulses. Picture a flawless symphony suddenly interrupted by a distant, off-tune vibration, not enough to drown out the music but impossible to ignore. At first, scientists suspected instrumental error or interstellar scattering, but the hum persisted across multiple observatories. That left one compelling culprit: plasma clouds drifting between the pulsar and Earth. These vast, turbulent regions of ionized gas don't just block or distort signals, they can delay them, bending radio waves like light through a funhouse mirror. The hum's irregularity hints at something even stranger. Most plasma-induced distortions are chaotic, but PSRB 1937 plus 21's fluctuations follow a rough pattern, rising and falling over months or years. This suggests the interfering plasma isn't just a diffuse fog. It might be structured, perhaps threaded with magnetic filaments or dense knots that act like cosmic tuning forks, resonating at specific frequencies. Some researchers propose these structures could be remnants of ancient supernova, lingering like ghostly cobwebs in interstellar space. Others wonder if they're evidence of nested plasma clouds, layered shells of ionized gas where each layer bends the signal slightly differently, creating interference patterns we perceive as a hum. What makes this enigma so tantalizing is how it blurs the line between noise and signal. The hum isn't just an obstacle to studying the pulsar, it's a message about the invisible medium it traveled through. By analyzing its ripples, astronomers can map the hidden plasma between stars, uncovering densities and magnetic fields no telescope could directly image. It's like listening to a conversation through a closed door. You might miss some words, but the echoes tell you about the room beyond, yet the deeper mystery remains. Why does this pulsar, one of the fastest and most stable ever discovered, hum at all? Most millisecond pulsars don't exhibit such pronounced timing noise. Could PSRB 1937 plus 21 be plowing through an unusually dense plasma pocket? Or is its extreme rotation rate somehow amplifying subtle interstellar distortions? The answers might rewrite our understanding of how signals traverse the galaxy's ghostly plasma highways. For now, the hum endures, a cosmic murmur reminding us that even the universe's most precise clocks don't tick in perfect silence. The Vela supernova remnant should be a graveyard, a quiet expanse of debris left behind after a star's catastrophic death. But something in this cosmic wreckage is still talking. Known as Vela Jr., this younger, fainter cousin of the main Vela remnant has been emitting gamma-ray bursts with spectral features so bizarre, they've left astrophysicists scratching their heads. These aren't the clean, predictable signatures of radioactive decay or particle collisions. Instead, they're jagged, uneven, almost as if something out there is tampering with the signals before they reach us. At the heart of the mystery lies plasma, superheated magnetized gas that fills the space between stars. When a supernova explodes, it doesn't just scatter debris, it sends shockwaves rippling through this plasma, accelerating particles to near-light speeds and twisting magnetic fields into knots. These shockwaves act like cosmic amplifiers, boosting faint emissions into detectable signals, but they can also distort them, warping their spectral fingerprints beyond recognition. Picture a pristine radio signal passing through a thunderstorm, emerging on the other side garbled and full of static. That's what might be happening to Vela Jr.'s gamma rays as they traverse a gauntlet of turbulent plasma left behind by the explosion. Yet the oddities run deeper. Some of these bursts exhibit line-like features, sharp spikes or dips in their energy spectra that shouldn't exist in such chaotic environments. Normally, gamma-ray spectra are smooth curves, shaped by broad physical processes like particle acceleration. The presence of these spectral lines suggests something more structured at work, perhaps plasma condensing into temporary, dense filaments that absorb or emit specific energies. It's like catching a glimpse of a hidden pattern in static, fleeting but impossible to ignore. One leading theory points to nuclear reactions reigniting in the remnant's ashes. As shockwaves sweep through the debris, they could compress pockets of leftover stellar material, triggering bursts of fusion that emit gamma rays with unique spectral signatures. But here's the catch. These reactions should produce predictable, well-understood patterns. Vela Jr.'s signals refuse to fit the mold. Some researchers speculate that exotic plasma physics like quantum turbulence or magnetic reconnection might be sculpting these emissions in ways our models can't yet replicate. Others float the possibility of an unseen compact object, a neutron star or black hole hidden within the remnant, stirring the plasma into irregular outbursts. The most tantalizing clue lies in the burst's timing. Unlike the steady decay of most remnants, Vela Jr.'s gamma-ray activity comes in erratic flares, with quiet periods punctuated by sudden, intense spikes. This isn't just a dying ember, it's a fire that keeps reigniting. Could plasma instabilities be stockpiling energy, releasing it in bursts when magnetic tensions finally snap? Or are we seeing the remnant interact with an unseen environment, like a dense interstellar cloud or dark matter halo that fuels these irregular eruptions? What makes Vela Jr. unforgettable isn't just the mystery of its signals, but what they reveal about the afterlife of supernovas. Even in death, stars don't just fade quietly. Their remnants seethe with activity, their plasma-choked ruins capable of twisting light, hiding objects, and rewriting the rules of high-energy physics. Every bizarre burst from this cosmic wreck is a reminder: the universe doesn't do tidy endings. It leaves doors ajar, whispers in the dark, and puzzles waiting to be unraveled. And sometimes the most unsettling signals aren't the ones we can't explain, they're the ones that refuse to stay silent. Fast radio bursts already rank among the universe's most perplexing signals. But when they arrive wearing an eerie polarized mask, they become something else entirely. Picture sunlight reflecting off a lake at dawn, its glare softened by sunglasses that filter out certain light waves. Now imagine that same principle applied to cosmic explosions, where magnetic fields twist radio waves into ghostly, spiraling patterns we call polarization. These aren't just aesthetic quirks, they're fingerprints of the chaotic plasma highways these bursts traverse, and they're rewriting how we understand the universe's most violent events. Take FRB 2019050b, a burst detected in 2019 that shouldn't have been visible at all. Its polarization was so extreme 99% of its radio waves aligned in a single direction that it defied every model of how cosmic plasma behaves. Normally, the turbulent soup of charged particles between galaxies scrambles polarization like a whirlpool shredding a paper boat. Yet this signal arrived with near-perfect clarity, suggesting it had punched through a region of space where plasma wasn't just chaotic but structured, its magnetic fields acting like a cosmic comb, grooming the burst's radio waves into uniformity. This is where plasma's hidden architecture comes into play. When fast radio bursts zip through the universe, they don't travel through empty space. They navigate a labyrinth of magnetized plasma filaments, remnants of ancient supernova or the faint glow between galaxies. These filaments can rotate the polarization of passing radio waves, a phenomenon known as Faraday rotation. The stronger the magnetic field and the denser the plasma, the more extreme the twist. But FRB 2019050b flipped the script. Instead of arriving scrambled, its polarization hinted it had passed through a rare, quiet zone, a pocket of space where plasma's magnetic fields were unnervingly calm, almost as if something had smoothed them. The implications are staggering. If vast regions of structured plasma exist, they could function as interstellar communication channels, natural fiber optic cables that preserve polarized signals across cosmic distances. But there's a darker possibility too. Some theorists suggest these ghostly polarized bursts might be the aftermath of colossal magnetic eruptions, like Magneta's neutron stars with magnetic fields 1 trillion times stronger than Earth's experiencing apocalyptic quakes. When such a star's crust fractures, it could launch a shock wave through its surrounding plasma, briefly aligning the chaos into a coherent magnetic corridor that polarizes any burst passing through it. Even more unsettling are the bursts that change polarization mid-flight. FRB 202000120E, detected in 2020, started with its radio waves neatly aligned, then abruptly switched angles halfway through its 3-millisecond duration. The only plausible explanation, the burst encountered two distinct plasma environments along its path. Imagine a beam of light passing through a waterfall, then a prism, emerging with its properties altered twice. This two-step polarization suggests the signal grazed the edge of a galactic halo, a vast, invisible cocoon of magnetized plasma surrounding a distant galaxy before plunging through a second turbulent zone. The real mystery lies in what these polarized whispers reveal about the universe's hidden scaffolding. Plasma accounts for 99% of the visible universe, yet we've barely begun to map its magnetic contours. Every twisted burst is like a flare illuminating the shape of these invisible fields, if only for a millisecond. And as astronomers collect more of these ghostly signals, a pattern emerges. The universe isn't just filled with plasma, it's shaped by it. Its hidden magnetic threads guiding, filtering, and sometimes obscuring the cosmic conversations we're only starting to overhear. Yet for all their clues, polarized fast radio bursts refuse to surrender their secrets easily. Some display polarization so pure, they challenge our understanding of magnetic field coherence across millions of light years. Others flicker with irregularities that suggest plasma isn't just a passive medium, but an active participant dynamically reshaping signals in real time. It's a reminder that space isn't empty, it's a living, twisting, electrified web, and we're only beginning to trace its threads. In 2015, astronomers caught something extraordinary, a fleeting but powerful radio burst emanating from the direction of Andromeda, our closest galactic neighbor. Unlike the usual cosmic static, this signal spiked sharply before vanishing within milliseconds, leaving behind more questions than answers. What made it remarkable wasn't just its origin, but its intensity, packing more energy than any natural source in Andromeda should theoretically produce. For a brief moment, it flickered like a beacon, then dissolved back into the cosmic background, as if the galaxy itself had whispered a secret we weren't meant to hear. The real puzzle lies in the signal's journey. Between Andromeda and Earth stretches a vast, invisible ocean of intergalactic plasma, thin, ionized gas that fills the voids between galaxies. Though this plasma is sparse, it's far from inert. Charged particles and magnetic fields twist through it, capable of bending and even amplifying radio waves under the right conditions. Some researchers suggest that what we detected might not have been the original signal at all, but a distorted echo, magnified by a fortuitous alignment of plasma clouds acting like cosmic lenses. Picture a flashlight beam passing through a hall of mirrors. The light reaches you, but its source and true intensity are impossible to gauge. Yet the amplification theory only deepens the mystery. If plasma clouds intensified the signal, what was the original source? Andromeda hosts no known objects capable of producing such a brief, energetic burst naturally. Magnetar's neutron stars with colossal magnetic fields could theoretically generate similar emissions, but none have been identified in Andromeda with the right characteristics. Another possibility is something more catastrophic, like a neutron star collision or a black hole's disruptive feast, events so rare they're almost mythical in their elusiveness. The signal's brevity adds another layer of intrigue. Millisecond bursts are hallmarks of fast radio bursts, but those usually come from billions of light years away, not a mere 2.5 million. Could intergalactic plasma have stretched and distorted a longer signal into this fleeting spike? Laboratory experiments show plasma can compress radio waves under certain conditions, turning a sustained transmission into a sharp, needle-like pulse. If true, Andromeda's whisper might not have been a shout after all, but a murmur warped by its voyage across the abyss. What lingers, though, is the unnerving possibility that we're missing the bigger picture. Plasma doesn't just distort signals, it can also cloak them. If the intergalactic medium is more turbulent than we realize, entire populations of similar bursts might be scattering or fading before they reach us. The Andromeda signal could be the exception, not the rule, a single note that slipped through the cosmic static, hinting at a symphony we're otherwise deaf to. For now, the 2015 burst remains a celestial riddle, a fleeting flare that refuses to fit neatly into any category. Whether it was a natural event twisted by plasma's tricks or something else entirely, one thing is certain: the space between galaxies isn't empty. It's a dynamic, electrified frontier where even the quietest signals can carry echoes of the universe's best-kept secrets. Some signals arrive like ghosts, clear, powerful, and utterly alone. Astronomers call them orphan transients, radio bursts with no visible counterpart, no glowing star or exploding galaxy to explain their sudden appearance. These signals defy the usual cosmic choreography where light and radio waves dance in sync. Instead, they flicker into existence on radio telescopes, leaving optical instruments staring at empty patches of sky. The question isn't just where they come from, but why we can't see their origins. The answer might lie in one of the universe's most elusive materials, plasma, and its uncanny ability to play cosmic hide and seek with light. Picture a dense nebula, its heart choked with superheated plasma. To visible light, this region is a brick wall. Photons slam into free electrons and scatter, absorbed or deflected before they can escape. But radio waves, they slip through like whispers under a door, their longer wavelengths navigating the plasma maze with ease. This selective transparency could explain why some radio bursts appear orphaned, their visible light snuffed out by intervening plasma clouds, while their radio signatures sail unobstructed to Earth. It's like hearing a concert through a thick curtain. The music reaches you, but the stage remains invisible. One of the most baffling examples is the transient discovered near the galactic plane in 2018. Designated ORT-1, it flared bright in radio observations, pulsing with the energy of a neutron star, yet deep optical scans revealed nothing but void. Follow-up infrared and X-ray telescopes joined the hunt, but the source stayed stubbornly dark. The leading theory, a magnetar, a highly magnetic neutron star, hidden behind a fortress of plasma, its visible light trapped in the very medium that lets its radio cries escape. But plasma doesn't just hide sources, it can create orphans. Turbulent plasma clouds occasionally emit their own coherent radio bursts through a process called plasma masering, where charged particles, accelerated by magnetic fields, amplify specific frequencies. These emissions mimic astrophysical transients but originate from diffuse, invisible structures, no central engine required. It's the difference between spotting a lighthouse and hearing a foghorn. One has a clear beacon, the other is just sound bleeding through the mist. The implications stretch beyond mere curiosity. If orphan transients are signals masked by plasma, they could be markers of the universe's densest, most magnetized regions, places where stars are born or black holes feed. Alternatively, if they're plasma masers, they might reveal entirely new physics, where clouds of ionized gas briefly organize into natural radio transmitters. Either way, these orphans aren't anomalies, they're clues. The cosmos isn't just sending us messages, it's teaching us how to listen in the dark. What makes these signals unforgettable is their defiance. They challenge the assumption that every radio burst should have a visible partner, forcing us to reconsider how energy moves through space. Plasma, often dismissed as interstellar static, emerges as a master illusionist, bending light and sculpting radio waves into puzzles we're only starting to solve. And as telescopes grow more sensitive, these orphans may prove to be the rule, not the exception, reminders that the universe speaks in many wavelengths, and some voices are meant to be heard, not seen. Kepler 438 should have been just another quiet red dwarf, a small, cool star with a single Earth-sized world orbiting snugly within its habitable zone. But in 2015, scientists noticed something unsettling. This star wasn't just flickering, it was screaming. Brief, violent radio flares erupted from its surface, some so powerful they dwarf our sun's most extreme solar storms. The strangest part, these flares didn't match the usual tantrums of a young, active star. They came in clusters with patterns that felt almost rhythmic, as if something, or someone, was tampering with the volume knob of the cosmos. At first glance, plasma storms seemed the obvious culprit. Red dwarfs like Kepler 438 are notorious for their turbulent magnetic fields, which can trap superheated plasma in twisting loops until they snap, unleashing bursts of energy. But these flares were odd. They peaked at frequencies typically associated with planetary auroras, not stellar activity. That raised a tantalizing question. Could Kepler 438 orbiting planet Kepler 438b be influencing the flares? If the planet had a strong magnetic field, its interaction with the star's plasma winds might generate radio emissions like a cosmic feedback loop. Picture the way Jupiter and its moon Io create intense plasma currents, sparking radio signals detectable across the solar system. Only here, the scale was unimaginably larger, with an entire star and its world locked in an electromagnetic dance. Yet some researchers hesitated. The flare's structure was too clean, their modulation too precise for natural plasma turbulence alone. One daring hypothesis suggested the signals might not be natural at all. Advanced civilizations, theorists speculated, could harness stellar plasma as an energy source, deliberately triggering flares to power planetary-scale technology. On Earth, we've experimented with plasma in fusion reactors. A civilization millennia ahead might manipulate it like a cosmic power grid. The flare's clustered timing could hint at energy extraction cycles, pulses synchronized to some unfathomable infrastructure hidden in the star's fiery grasp. Skeptics countered fiercely. Plasma, they argued, is chaos incarnate. Its behavior under extreme magnetic stress can mimic patterns we'd mistake for intelligence, especially across interstellar distances. The star's flares might simply reflect an unknown plasma instability, a quirk of red dwarf astrophysics we haven't catalogued yet. After all, Kepler 438 is older than our Sun. Its inner workings could harbor phenomena alien to our understanding. The debate crystallizes around one haunting detail. Kepler 438b is right in the habitable zone, a world bathed in starlight, potentially ripe for life, yet lashed by flares fierce enough to strip atmospheres. If nature alone is responsible, it's a brutal twist of fate. But if something else is shaping those flares, something purposeful, the implications rewrite not just our search for aliens, but our understanding of how civilizations might sculpt their cosmic environments. For now, Kepler 438 radio flares remain an open case, a stellar Rorschach test revealing as much about our hopes as the universe's mysteries. Every new observation peels back another layer, leaving us to wonder, are we hearing the roar of an angry star or the hum of a machine we've yet to comprehend? Deep in the small Magellanic Cloud, a cosmic beast stirs. The Dragon's Egg Nebula, officially known as N76, isn't just another stellar nursery. It's a radio pulsar unlike anything else in the known universe. While most nebulae glow with the chaotic light of newborn stars, this one breathes. Every 23 minutes, like clockwork, it emits a pulse so precise you could set your watch to it. But here's the twist, there's no pulsar at its heart, no spinning neutron star to explain the rhythm. Instead, the entire nebula itself seems to be singing, its emissions rising and falling as if orchestrated by some unseen conductor. The key to this enigma might lie in the nebula's tangled nest of plasma filaments. These supercharged tendrils, stretching light years across the cloud, aren't just passive decorations, they could be functioning as nature's own antenna array. When plasma flows along magnetic field lines, it can generate coherent radio waves, much like electrical currents in a human-made antenna. But in the dragon's egg, the scale is almost unimaginable. Picture a harp with strings made of ionized gas, each one vibrating as stellar winds and radiation buffet them. The combined effect could produce those eerily regular pulses, as if the nebula itself is tuning into some cosmic frequency. Yet the mystery deepens when you examine the signal's structure. Unlike the clean, sharp pulses from a neutron star, the dragon's egg's emissions have a textured, almost organic quality. Subtle harmonics and secondary peaks that suggest multiple filaments resonating in concert. Some researchers propose this could be evidence of plasma loops snapping and reconnecting in unison, a phenomenon normally seen in solar flares but magnified to nebular proportions. Others speculate that the nebula's central star, a hot, massive giant named AB7, might be stirring the plasma like a spoon in a swirling cup, creating standing waves that reinforce the pulse every cycle. The most tantalizing possibility that we're witnessing a new form of astrophysical feedback, as AB7 fierce ultraviolet radiation ionizes the surrounding gas. It could be triggering cascades of plasma oscillations that bounce back toward the star, only to be energized again in an endless loop. This wouldn't just explain the rhythm, it'd reveal a previously unknown way for stars and nebulae to communicate not through gravity or light, but through the choreographed dance of charged particles. What makes the dragon's egg unforgettable isn't just the signal, but what it implies about plasma's hidden potential. We've long treated these ionized clouds as cosmic afterthoughts, the static between stars. But here, they're the lead performers, shaping energy into patterns that defy our expectations. Every pulse is a reminder the universe doesn't need a neutron star to keep time. Sometimes all it takes is a storm of magnetized gas, vibrating in the dark. Rising from the heart of the Milky Way like two colossal hourglasses, the Fermi bubbles stretch 50,000 light-years across towering structures of gamma-ray energy that defy easy explanation. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these gargantuan formations glow with the aftermath of some ancient cataclysm, possibly a frenzied feeding spell by our supermassive black hole, Sagittarius A. But nestled within their shimmering boundaries lie fainter, more elusive whispers, radio signals that pulse and flicker as if carrying fragments of a story we've only begun to piece together. These echoes aren't uniform, they arrive scrambled, their frequencies stretched and compressed like a tape recording played at inconsistent speeds, the culprit. Plasma winds rivers of charged particles racing outward from the galactic center at millions of miles per hour. As these winds tear through the bubble's outer layers, they churn the surrounding plasma into turbulent whirlpools, twisting any signals that pass through them. Imagine shouting into a hurricane. Your words might reach the other side, but fractured, distorted, barely recognizable. That's the fate of these gamma-ray echoes, their origins obscured by the very medium that carries them. Yet the distortions themselves might hold clues. By analyzing how the signals warp, astronomers can map the invisible structure of the bubble's plasma currents. Some echoes exhibit bizarre Doppler shifts, sudden spikes in frequency suggesting they've skimmed the edges of concentrated plasma jets, regions where magnetic fields funnel particles into focused beams. Others smear across the radio spectrum, hinting at zones where the plasma froths chaotically, like ocean waves crashing against a cliff. These variations paint a portrait of the bubbles not as static relics, but as dynamic, ever-shifting entities, their inner weather systems sculpted by forces we're only starting to grasp. The biggest mystery isn't just how these signals are altered, but why they exist at all. Gamma rays typically don't produce coherent radio echoes unless some intermediary process converts their energy into longer wavelengths. One compelling theory involves dark accelerators, hypothetical regions within the bubbles where plasma turbulence reaches such extremes that it acts like a natural particle collider, smashing electrons and positrons together to generate secondary radio emissions. It's as if the bubbles aren't just glowing with leftover energy, but actively processing it, cooking up new signals in their swirling depths. Then there's the eerie timing. Some echoes arrive in clusters, spaced weeks or months apart, as if triggered by periodic surges in the galactic core's activity. This has led to speculation that the bubbles might be resonating, vibrating like colossal bells struck by gravitational waves from Sagittarius A's occasional feast. If true, the echoes could be more than just static. They might be a form of cosmic sonar, revealing the black hole's past eruptions in ways light alone cannot. But perhaps the most tantalizing possibility is that we're hearing echoes of multiple events layered atop one another. The bubbles are thought to be millions of years old, their expanses littered with the remnants of countless outbursts. A single radio echo might actually be a chorus faint, overlapping signatures from different eras, each warped by the plasma winds of its time. Untangling them would be like listening to a symphony where every instrument plays a different measure, yet somehow the music never stops. What's clear is that the Fermi bubbles are anything but silent. Their whispers, though faint, chronicle the violence and beauty of our galaxy's central engine, a story written in gamma rays, encrypted by plasma, and waiting for us to decode its next chapter. Every echo is a ripple in the cosmic pond, and we're only just learning how to read the waves. When Oumuamua streaked through our solar system in 2017, it wasn't just its bizarre shape, a 600-foot-long cosmic cigar tumbling end over end that sparked debate. Long after it vanished beyond Neptune's orbit, whispers lingered about something even stranger, faint radio signals allegedly detected in its wake. Claims circulated that this interstellar visitor might have been more than a peculiar rock, that its unusual acceleration could hint at artificial origins, even technological ones. But the truth, as often happens in astronomy, is tangled in the invisible embrace of plasma. The signals in question weren't direct broadcasts from Oumuamua itself. Instead, they emerged from Earth-based radio telescopes as anomalies in the background, static subtle spikes that some argued aligned with the object's trajectory. Skeptics quickly pointed to a far more mundane explanation, the plasma sheath effect. When an object moves at high speeds through the interstellar medium, it doesn't travel through empty space. It plows through a thin soup of ionized particles, compressing and electrifying the plasma around it like a boat churning wake in water. This creates a temporary, charged envelope, a natural radio amplifier that can distort or even mimic artificial signals. Here's where things get wild. Plasma sheaths don't just passively surround fast-moving objects, they interact with them. As Oumuamua tumbled, its rotation would have caused variations in the sheath's thickness and density, potentially generating low-frequency radio emissions as the plasma constantly rearranged itself. These emissions wouldn't be deliberate transmissions, but cosmic static, like the crackle of a ship's hull scraping against waves. The real twist, these very emissions could explain Oumuamua's disputed non-gravitational acceleration. Outgassing the traditional explanation would have left visible traces, but none were found. A plasma-induced push, however, might have nudged the object subtly, no comet-like venting required. But why would a natural plasma sheath produce signals that seemed structured? The answer lies in chaos. Turbulent plasma can form transient, coherent structures, brief moments where charged particles align just right to emit narrowband radio waves, mimicking the hallmarks of intentional signals. It's the universe's version of pareidolia, where we hear a voice in white noise or see faces in clouds. Our instruments, fine-tuned to filter cosmic noise, might latch onto these fleeting patterns, amplifying them into false positives. The lesson of Oumuamua's phantom signals isn't just about debunking, it's about recalibration. As we scan the skies for interstellar visitors, we're learning that plasma isn't just background interference. It's an active participant in the conversation, capable of warping, amplifying, or inventing signals where none exist. Every strange pulse, every anomalous blip must now pass through this new filter. Is it a message, or just the universe's way of whispering in a language we're still learning to decode? Deep in the cosmic static, where ordinary physics starts to fray, there's a whisper that shouldn't exist. It's not from stars, not from black holes, not even from the swirling plasma we've come to expect as the universe's background noise. This signal is different, faint, diffuse, and seemingly tied to the most elusive substance in existence, dark matter. For decades, dark matter's presence has been inferred only by its gravitational grip on galaxies, a ghostly hand bending light and skewing orbits. But now, a handful of bizarre radio emissions scattered across the sky like cosmic breadcrumbs hint that dark matter might be speaking in a language we're only beginning to hear. These signals don't behave like anything else. Some appear as low-frequency hums resonating across galaxy clusters where dark matter is thought to gather. Others flicker like distant lighthouses, their pulses too regular to dismiss as random noise, yet too faint to trace to any known source. The most compelling of these anomalies comes from a quiet patch of sky near the constellation Auriga, where radio telescopes have picked up a peculiar oscillation, a wave-like distortion that seems to align with theoretical predictions of how dark matter might interact with plasma under extreme conditions. Here's where the speculation ignites. If dark matter particles, whatever they are, collide or decay within vast clouds of interstellar plasma, they could theoretically release energy as radio waves. Picture a stone dropped into a pond. The ripples are the energy dissipating. Now imagine that stone is made of something invisible, and the pond is a sea of supercharged particles. The resulting waves wouldn't look like anything natural because we've never seen dark matter do anything before. That's why these signals, tenuous as they are so electrifying. They're not just anomalies, they're potential fossils of an unseen universe flickering into view. The controversy lies in the interpretation. Skeptics argue these signals could be artifacts of plasma turbulence, twisted beyond recognition by magnetic fields or cosmic rays. After all, space is full of phenomena we don't fully understand. Why jump to dark matter? But proponents counter with the signal's peculiar fingerprints. Some exhibit spectral features that don't match any known astrophysical process, like a radio broadcast tuned to a frequency no natural transmitter should use. Others cluster in regions where dark matter is predicted to be densest, as if tracing an invisible scaffold woven through the cosmos. The boldest theories suggest plasma could act as a dark matter antenna. In certain high-energy environments like the outskirts of black holes or the hearts of merging galaxies, plasma's chaotic dance might briefly unlock dark matter's secrets, converting its hidden energy into detectable radio whispers. It's a long shot, but if true, it would mean we're not just hearing noise. We're eavesdropping on a conversation between the universe's two most dominant yet mysterious substances, one we can't see and one we can't fully comprehend. For now, these signals remain on the fringe, too strange to ignore, too ambiguous to confirm. But they linger in the data, teasing us with the possibility that dark matter isn't just a silent spectator. It might be humming ever so softly, waiting for us to fine-tune our ears to the static. And if we do, we won't just solve a cosmic mystery, we'll crack open a door to a reality we've never been meant to see. From the WOW signals electrifying 72 seconds to the rhythmic pulses of NGC 253's celestial lighthouse, each of these 25 cosmic whispers carries a story tangled in the invisible threads of interstellar plasma. These clouds, far from being silent backdrops, shape, distort, and sometimes even invent the signals we detect, turning straightforward transmissions into riddles. The Lorimer Burst's raw power might have been magnified by plasma lenses, while SHB02 plus 14A's drifting tones could be the result of charged particles warping its path. Even the Fermi bubble's ghostly echoes are sculpted by plasma winds, their messages scrambled across 50,000 light-years. What's startling isn't just the variety of these signals, but how plasma consistently blurs the line between nature and something more. It can make a microwave's radiation mimic an alien broadcast, twist a magnetar's scream into a harmonic hum, or cloak an entire civilization's transmissions behind a veil of ionized fog. The universe, it seems, is a master illusionist with plasma as its favorite sleight of hand. Yet this isn't just a tale of cosmic static. Every distorted signal, every anomalous burst is a challenge, a dare to look deeper. For all our telescopes and algorithms, we're still learning to listen past the plasma's whisper, to separate the universe's true voice from the noise. And that's the thrill. The next signal we catch might be the one that slips through undistorted, a clean message in the chaos. Or perhaps it'll be even stranger, a pattern so deliberate it defies all natural explanation. That's the beauty of the unknown. It doesn't just test our science, it sparks our imagination. So keep watching the skies and the comment section. What do you think these signals mean? A cosmic weather report, a beacon, or something we haven't even dreamed up yet? Drop your wildest theories below, and let's keep decoding the universe together. After all, the next transmission could change everything.